Another method to prepare carboxylic acid is by the oxidative cleavages. The first method is the oxidative cleavage of alkenes and alkynes. When asymmetrical alkenes is heated in presence of alkaline potassium permanganate, then the mixture of carboxylic acids are formed. For example, when pent-2-ene is heated in presence of alkaline potassium permanganate, then the mixture of acetic acid and propionic acid is formed. The oxidative cleavage is also carried out by reaction of alkene or alkynes with ozone in presence of hydrogen peroxide. Unsymmetrical alkene like pent-2-ene, when reacts with ozone in presence of hydrogen peroxide, gives the combination of acetic acid and propionic acid, whereas when unsymmetrical alkyne like pent-2-ine reacts with ozone in presence of hydrogen peroxide, gives the combination of acetic acid and propionic acid by oxidation of alkyl benzene. Aromatic carboxylic acids can also be prepared by the oxidation of an alkyl group attached to the benzene nucleus, which will be oxidized to carboxylic group irrespective of the size of the alkyl group. C6H5CH3, when oxidized in presence of potassium permanganate and NaOH or alkaline potassium permanganate, gives benzoic acid. This reaction is also carried out in presence of acidified potassium dichromate. Paraxylene CH3 C6H4CH3, when oxidized in presence of acidified potassium dichromate, gives terephthalic acid. Aromatic carboxylic acids can also be prepared by Friedel-Crafts reaction and hydrolysis of the side chain halogen derivatives. Benzene C6H6, when reacts with carbonyl chloride COCl2 in anhydrous AlCl3 medium, gives benzoyl chloride C6H5COCl, which further undergoes hydrolysis to give benzoic acid C6H5COOH. It is very important to remember here that during the reaction, carbonyl chloride should be used in excess, otherwise benzophenone may be formed as the main product. Just consider the reaction where benzene reacts with carbonyl chloride in a limited concentration. C6H6 plus COCl2, where COCl2 is in limited concentration, reacts with anhydrous AlCl3, gives benzophenone C6H5CO C6H5, and few molecules of HCl are formed. Benzoic acid can also be prepared by treating benzotrichloride with aqueous NaOH. Benzotrichloride on reaction with aqueous NaOH gives an intermediate and unstable trihydroxybenzo compound which loses water molecules to give benzoic acid. Remember that the presence of more than 2 hydroxy group on a single carbon atom always releases water molecules, properties of carboxylic acids. The compounds from this group shows a very unique and interesting properties, like the first 3 members of this group containing carbon 1 to carbon 3 are colorless, pungent smelling liquids. The next 3 containing carbon atoms C4 to C6 have unpleasant odors. Acids with 7 or more carbon atoms have no distinct smell because of low volatility. Now, the next property of carboxylic acid is the compounds containing up to 5 carbon atoms are freely soluble in water due to the hydrogen bonding with water molecules. The solubility of higher membranes decreases rapidly with the increase in size of the alkyl group due to increased influence of the hydrocarbon part, which is non-polar and lyophobic. Lyophobic means water heating. Benzoic acid is nearly insoluble in cold water because here also the hydrocarbon part C6H5 outweighs the influence of polar part. Boiling point of carboxylic acids, particularly lower membranes, are higher than alcohols of comparable molecular masses. The higher boiling point, that is low volatility of lower carboxylic acids including benzoic acid, is due to the fact that the hydrogen bonding in carboxylic acid is stronger due to the formation of a ring than those of alcohols. These carboxylic acids exist in dimers. The behavior of methanoic acid or formic acid is very exceptional, and it exists as dimer in vapor state and as polymer in liquid and solid states. In normal carboxylic acids, the compounds containing even number of carbon atoms have markedly higher melting points than the odd members preceding or following it. This property is known as alternation effect or oscillation effect. This is because in case of even member acids, the carboxyl and the terminal methyl groups are on opposite sides of the zigzag carbon chain and hence fit better in the crystal lattice. This results in increase in intermolecular forces, which in turn increases melting point. On the other hand, the odd member acids have carboxyl and terminal methyl group on the same side of the zigzag chain,